To test the extreme limits of neural network compression, we start with a standard dense MNIST digit classifier. The architecture maps 784 input pixels through a 128-node hidden layer, down to a 64-node layer, and finally into 10 output logits representing the digits 0 through 9. In a standard neural network, this geometry contains over 100,000 continuous free parameters. During training, backpropagation incrementally adjusts every single one of those floating point weights to minimize error. This experiment intentionally breaks that mechanism. In this proof of concept, weights are never treated as free parameters. They cannot be individually adjusted, and they never drift. Instead, every weight matrix in the network is strictly generated from a deterministic pipeline. A single 64-bit integer, a layer seed, is passed through a He initialization pseudo-random number generator. That generator outputs a complete static matrix of weights. By enforcing this constraint across the entire architecture, the physical footprint of the final trained network is decoupled from its node count. We don't save a massive binary blob of weights. The entire network checkpoint is a tiny JSON file containing exactly 3 integers. Compressing the model into 3 discrete seeds creates a unique optimization problem. Gradients do not exist in this highly restricted space. You cannot calculate a partial derivative with respect to a pseudo-random integer. To train this architecture, we have to evaluate 3 distinct black box search strategies, testing exactly how far a deterministic seed to weight map can be pushed as a neural genome. Forcing a continuous parameter space into a procedural initialization demands an entirely non-differentiable approach to optimization. The system has to find the right mathematical recipe, not sculpt the weights. A network initialized with random seeds correctly classifies MNIST digits roughly 10% of the time. With 10 possible output classes, this is equivalent to random guessing. Measuring improvement during search requires a granular signal, and hard accuracy fails to provide one. A single bit flip in a 64-bit seed will drastically alter the generated weights, but it rarely changes the final argmax classification of a batch. The accuracy stays flat, offering 0 optimization signal to the algorithm. To rank random seeds within a batch, the system relies on a continuous metric called soft fitness. This chart maps the difference between our available signals. While hard accuracy remains stepped and unresponsive, soft fitness provides a smooth, continuous downward curve that tracks micro-improvements in the network's confidence. The score is calculated using 2 mathematical components: standard softmax negative log likelihood and a specialized margin penalty. The margin penalty forces the loss dial to move even when the network is entirely wrong. It calculates the distance between the correct target logit and the highest incorrect logit. If a bit flip brings the correct answer slightly closer to the top, the penalty shrinks. This establishes a clear directional rule for the search algorithm. A lower soft fitness score mathematically indicates a warmer physical recipe for the generated weights. Without this continuous loss surface, an inherently discrete genome offers no path forward. The search would remain blind to any incremental progress. The first search algorithm tested on this continuous loss surface is warmth mode. This is a single genome hill climbing strategy that attempts to incrementally improve one set of seeds. During each epoch, the system isolates one layer at a time and systematically probes all 64 possible bit flips for its seed. It measures the resulting change in soft fitness for every single flip, compiling a warm bitmap to track improvements. Then, the system biases its random mutations exclusively toward the warm bits, combining the toggles that yielded positive deltas. It also employs an antithetic testing mechanic, simultaneously jumping the integer value by a positive delta and a negative delta. It compares both directions and keeps the one that provides the steepest local improvement. The empirical logs for this approach show immediate but limited gains. The soft fitness slowly improves, and the network climbs out of random chance, but the full validation accuracy peaks and permanently stalls at approximately 15%. The failure mode is visible directly in the console output. The warm bits rapidly go cold. Once the immediate 1-bit neighborhood around the seed is fully exhausted, no single toggle offers an advantage, and the algorithm becomes stuck. Single-point linear hill climbing lacks the representational capacity to navigate this space. A highly restricted manifold requires a mechanism to jump across valleys of poor performance, rather than just walking uphill. To bypass local minima, the experiment shifts to a second algorithm, Mode 2, or clustered DNA. This mode expands the scope of the search. Instead of optimizing a single integer locally, a full population of genomes evaluates multiple positions at once. All 3 layer seeds mutate and move concurrently. The architecture uses an island model topology. The total population is divided into 4 independent clusters, with 6 active genomes operating inside each cluster. Within these clusters, a clear hierarchy dictates movement. The genome with the best batch soft fitness score is mathematically designated as the local elite. The remaining genomes update using a bitwise crossover equation. Standard genomes are pulled toward their local elite's DNA structure, adopting chunks of the highly performant seed while applying random mutations. Every few generations, the clusters trigger a migration mechanic. A standard genome from one cluster is swapped into a neighboring cluster, cross-pollinating genetic traits and preventing isolated islands from stagnating. This clustered approach yields a higher ceiling. Over successive generations, the Hall of Fame validation accuracy climbs steadily, reaching a peak of 18.8%. By maintaining isolated pockets of mathematical diversity, distributed exploration via parallel attractors succeeds where local hill climbing fails. The system is able to evaluate multiple promising recipes simultaneously. Evolutionary population models carry an inherent flaw. If a particular elite is too successful, the crossover equation pulls every other genome toward it until the entire cluster converges into exact clones. The population loses diversity, and the search freezes. The system combats this by actively measuring clone density. It calculates the mean pairwise DNA cosine similarity between every node. When the cosine similarity metric exceeds 0.85, the system registers an imminent cloning failure. The cluster is collapsing. In response, the algorithm dynamically adjusts its behavior. It severely restricts the mathematical pull toward the elite genome and simultaneously cranks up the baseline mutation rate, forcing the nodes to scatter back into the search space. If the collapse is severe enough, it triggers a secondary response. The system injects entirely fresh, randomized immigrant genomes directly into the cluster to forcefully reintroduce vital mathematical diversity. Crucially, while soft fitness drives the localized pulling within a batch, the system relies strictly on stable, full validation accuracy to lock the Hall of Fame. Batch fitness is too noisy, a lotto ticket metric that fluctuates constantly. Only a full validation pass can confirm a genuine architectural improvement. Actively measuring and penalizing mathematical similarity proves to be just as critical to traversing discrete spaces as the objective fitness function itself. You have to force the system to search wide, not just deep. To understand exactly which physical components are responsible for that 18.8% peak, the experiment enters its final phase, a coordinate descent strategy designed for precise ablation. Coordinate isolation freezes integer seeds for layers 1 and 2, locking initialized weights. DNA clusters operate entirely on layer 0. In round 1, manipulating layer 0 pushes validation accuracy from 15.2 to 17.3%. Round 2 secures a Hall of Fame latch at 18.3%. The critical discovery occurs when the focus shifts. Searching the seed space for layers 1 and 2 yields absolutely no improvement over their original chance-based topological initialization. The final checkpoint JSON reflects this physical reality. The entire predictive power of the network is derived from altering just the very first layer's integer. The subsequent layers remain entirely random. By isolating variables, the mathematics prove that the entire leap from random chance to peak accuracy was extracted from a single algorithmic dimension. Only one Hay initialization recipe actually learned the dataset. This physical change in the network's predictive geometry is verified by Loom's deviation metrics heat maps, shown here. The quality score shifts demonstrably from a starting baseline of 39.6 up to a trained peak of 44.5, proving the distribution of errors has structurally improved. However, reaching an 18.8% peak accuracy with integer seeds must be contextualized. A standard backpropagation setup running on this exact same architecture would routinely achieve accuracy exceeding 95%. The gap reveals a core theoretical concept, the representational ceiling of the seed manifold. A randomly generated Hay initialization recipe possesses a hard mathematical limit in its capacity to map complex features. No matter how thoroughly you search the space of 64-bit integers, a single procedural seed cannot perfectly arrange a matrix to recognize the intricate nuances of handwritten digits. The architecture forces the system to search for an optimal initialization recipe, rather than actively sculpting continuous, non-differentiable weights to fit the data. It is selecting from pre-rendered shapes, not molding clay. While deterministic seed constraints are functionally viable for extreme network compression, unlocking competitive generalization intrinsically requires continuous, freely drifting parameter spaces. The three integers can find the right neighborhood, but they cannot cross the finish line.